Welcome to Calculus. Today we will investigate differentiating polynomial functions using the chain rule. Let's take a look at three examples. Our first example is the function y equals parentheses x squared plus 3 all to the power of 4. Just to make a case for why we need the chain rule in this case, I really can't differentiate this function without expanding it. So one view of this is I could take the strategy where I actually distribute this x squared plus 3 and multiply that binomial 4 times. But even as I write it out, you get the sense that that really is a lot of work and a lot of time spent to differentiate something that I have really a rule for. So I'm not going to take that route. I don't want to distribute that out. Instead, I want to consider this as a composite function f at g of x. So just to make a case here, what we're saying is we have a function f of x, which is simply some base, and I'm just going to let that be called x to the power of 4. We're calling the inside, what I've replaced with x here, g of x. And that's the function on the inside of the parentheses, x squared plus 3. So basically, what we're considering y to be here is, in fact, f of g of x, a composite function. And I'll write it in that way. So of course, the f of x is just x to the power of 4, but I'm replacing that domain with the range of g, which is x squared plus 3. So that kind of gives a background about really what case of polynomial function requires use of the chain rule. Well, let's define the chain rule using that same idea of composition. So the chain rule makes this claim. It says if you do have this instance where you've got f of g of x, and that's your function, the derivative of f of g of x is given as follows. So this is actually how we'll apply this chain rule. So it equals the derivative of f with g of x unchanged. So in one instance, we'll just take the derivative without changing the inside, the g of x at all. And then we're going to multiply times the derivative of g of x. So let's apply that here to this first example. So I'm going to take our function here, y equals parentheses x squared plus 3 to the power of 4. We've already kind of defined the parts. All we need to do is apply it at this point. So I'm going to rewrite it here with the derivative. So f, in fact, I'm just going to call it y prime. And so I'm going to take the derivative of f first. So I'm going to really take that 4 down as a coefficient. And I'm going to bring the power down by 1. But what I got to note is that I'm not changing the g of x function at all. That's still going to be x squared plus 3. Now, on the outside, I need to take the derivative of g of x, the stuff that's written in red. So that's going to be 2 times x to the power of 2 minus 1. And then the derivative of 3 is 0. And that's really the application of the chain rule. At that moment, I just need to simplify my expression. So y prime is 4. And I'm going to put this simplified version of the derivative of g. So 2x, it's going to just reduce to 2x times, again, x squared plus 3 to the power of 3. And as a final step, I will go ahead and record this as the product. So that's going to be 8x times parentheses x squared plus 3 all to the power of 3. And that is our final answer for the derivative. Let's take a look at a second example with a different type of exponent. So that first example had a positive integer exponent. Let's take a look at an example where the exponent's a negative integer. So this is f of x equals parentheses 5x to the power of 4 plus 2, all to the power of negative 5. So just again, to define this in terms of a composite function, this is f at g of x and the f function is this larger parentheses to the power of negative 5. The g function is the interior, the polynomial 5x to the power of 4 plus 2. So again, let's just remember what our chain rule says. If I've got that arrangement, f of g of x, the derivative of that function is going to be equivalent to the derivative of the f function with g of x unchanged on the interior times the derivative of the interior. So again, we'll just apply that rule to differentiate this example number 8. So I'm going to bring that power down. Negative 5 becomes a coefficient. The interior remains unchanged, and I'm going to take the power down by 1. So what you notice is that even though this is a negative power, the steps in terms of differentiating are the same. And then on the exterior, I need to multiply by the derivative of 5x to the 4th plus 2. So that's going to be 5 times coefficient 4, bring the power down by 1. And then the derivative of 2 is going to be 0. So at that point, again, I just need to simplify. So I've got negative 5, and then I'll bring the derivative of g, so that's 5 times 4 is 20. X to the power of 4 minus 1 is 3. Parentheses to the power of negative 5 minus 1 will be negative 6. And within the parentheses, 5x to the power of 4 plus 2. And as a final step there, we just multiply out. That's negative 100 x cubed, parentheses 5x to the power of 4 plus 2, all to the power of negative 6. So bottom line, for different types of exponents, we just really apply them the same way. We just have to be mindful of the sign if it's negative. Let's take a look at a third and final example here, where we look at a fractional or rational exponent. Here is our example number 9. Here we've got f of x equals parentheses 2x plus 1 to the power of 1/5. So just to, again, make a case about what our function is defined in terms of a composite, f at g of x in this case is going to be the f function, which is the bigger structure to the power of 1/5, and the g function is going to be 2x plus 1, the interior there. So if I'm applying the chain rule, we just, again, need to remember what it says. It says that if I've got that set up with a composition, and I'm taking the derivative of f of g of x, what that'll equal is the derivative of f with g unchanged times the derivative of g of x. And I think, just to correct a detail here, I should put that differentiation at the end, just to indicate I'm taking a derivative of the composition. Okay, so let's apply the chain rule. We'll set it up so the derivative of f of g of x is going to be equal to, so I'm going to take the derivative of the larger structure. So the 1/5 power, just the same, comes down out front. And then I'm going to bring it down by 1. So I'm going to subtract 1 from 1/5. I could write it as 1. I'm going to convert it to 5 over 5 to help with the subtraction. 2x plus 1 places right there in the interior, and then I need to take the derivative of that 2x plus 1 on the outside. So that's just going to be 2 times 1 times x to the power of 1 minus 1. And then to finalize that derivative, we would just bring the product here, 2 times 1. It's really just 2. And place 2x plus 1, that g of x in the interior, and then complete that subtraction of the powers. So that's going to be negative 4/5. And finalized, our derivative here is going to be 2/5 times base 2x plus 1, all raised to the power of negative 4 over 5. And that completes our derivative of this function f of x in number 9. One note here, remember that fractional or rational exponent could be recorded as a radical, the 5th root. So just to be aware that if you're looking at a radical function, it really is equivalent to a polynomial that has a rational exponent. Well, thank you for joining for these 3 examples, applying the chain rule to differentiate polynomial functions. See you soon.